Hi everybody, welcome back. We're continuing our Chapter 8 notes on work and energy. In our previous section we got through kind of the introduction of this chapter and defining what work and energy are. Particularly work we defined as being force applied over a distance. Now that you could call that delta x, you could call it delta y. It's just some sort of a distance or displacement. But just generically we call it d. Force times the distance times the cosine of the angle phi right here. That's the angle phi is the angle between the force vector and the displacement vector, or the distance vector. All right, so let's take that and let's go ahead and apply that to example 8.1, and then we'll do some other examples as well. So we've got an intern pushing a 72-kilogram patient on a 15-kilogram gurney, producing an acceleration of 0.6 meters per second squared. The question is, how much work does the intern do by pushing the patient and the gurney through a distance of 2.5 meters? Okay, so that's our distance d right there. We have our acceleration right here, and we have a mass of the patient as well as the gurney. Well, let's go ahead and, first of all, I'm going to make some more room for myself. So I'm going to shrink that down and put that right up there. We don't have a force, do we? However, we do know, because of Newton's second law, that force equals mass times acceleration. All right? So we can say, all right, well, the force applied by the nurse is the mass of the person plus a cart. All right, so that's mass of the person plus mass of, I shouldn't call it a cart, I guess it's a gurney. Gurney times the acceleration which we are given. All right, and of course, if work equals force times distance, we know that distance times a cosine of the angle phi. Well, what is the angle phi between the displacement and the force being applied? Well, there is no angle. Well, there is an angle, but they're basically the same, right? It's 0. So if phi is 0, phi being is 0 degrees, then that should maximize the force that is applied in the direction of motion right there. You know that the cosine of 0 is 1, and you can't get a cosine of anything bigger than 1. So the work is going to be our force. What's our force? It's the mass of the person or the patient plus the mass of the gurney times acceleration times the cosine of phi, which is really 0 degrees. All right, so let's go ahead and just substitute in right there. What's the mass of our person, of our patient? That's 72 kilograms plus, I believe, 15 kilograms times our acceleration. That is 0.6. So not accelerating very quickly. 0.6 meters per second squared times the cosine of 0 degrees, which of course you know is equal to 1. All right, so what do we get? I get a total of 52.2 what? Well, it's work, and so work is measured in joules, so that's going to be our unit right there. All right, the work that the nurse does, right there, 52.2 joules. Again, that will change if there is some sort of angle or other angle other than 0 between the force and the displacement or the distance, but this being 0, it's just going to wind up making everything go to 1. So that's our example 8.1 right there. Pretty easy, just a basic application of our work equals force times distance times cosine of phi. Let's go on to example 2. All right, here we have one where it is slightly different in that the work done by gravity's doing work for us, is in a different direction than the direction of displacement of this boat right here. So we call this a gravity escape system. It's probably just a fancy way for saying a ramp. A lifeboat moves down this ramp on a large ship, and then it free falls into the water below. Well, we don't care about the free fall. All we care about is the life raft moving down this ramp right here. Okay, so the mass. Let's go ahead and write this down. In fact, I'm going to make this smaller. No, in fact, I'll write it first. Mass of the lifeboat is 4,970 kilograms, so that's like 2.5 tons. The distance, d, equals 5.0 meters, 0.00 meters down the face of the ramp, okay? And dropping a vertical height of 2.5 meters. That's interesting. Why would we need that? Why would we need the vertical height, 2.5 meters? Well, we need that because we don't know the angle between the direction that the life raft is moving and gravity, which is doing the work, right? I mean, we're not doing the work, gravity's doing for us. So the question is, how much work does gravity do on the boat right here? Well, first thing we need to figure out is what is phi. Now, again, here it's marked as theta. It's perfectly fine, all right? But to be more specific, we want phi to be the angle between our displacement and the work or the force that is being done. In this case, the force is the weight force. All right, so all these thetas should really be phi right there. If we can find out that, we know our displacement, we know our mass, we should be able to figure out what the work that is being done is. All right, so let's find out what that is. So we have this triangle right here, this right triangle. How do we find out phi? All right, well, so we have a hypotenuse. Well, actually, if we were to turn this sideways, let's say take that and turn that, I'm going to write it down here in the lower, I'll write it right here. So that's our D and this right here. So I'm turning this 90 degrees counterclockwise. So that's our mg right there. See what I did right there? Okay. Wait a second. I shouldn't call that mg. What should I call that? This is our distance d down the face of the ramp, so that's that. Instead of mg, it's marked mg right here, but what is that really? That's really the height, right? That's the height that it falls through, or that delta y. So, excuse me for, that should be delta y. Right? So why are we doing that? Why are we setting it up like that? Well, remember, we need to find that angle between the work that is being done. By the way, mg, or the weight force right here, is being done in the direction of delta y, the change in y. But the displacement down the ramp is some angle from that, so we want to find out what that angle is. All right, so what is this angle phi in here? That's what we want to know. Well, we have an angle phi. We have an adjacent side, that's the delta y, right? And we have a hypotenuse, so what would that be? Adjacent hypotenuse, that would be cosine, right? So the cosine of phi would be our adjacent, I'll make that red because it already is red. Our adjacent side is delta y, and our ramp side is d, right? So we can say that phi, I'm running out of space here already, so that phi itself is going to be the inverse cosine, that's not a cosine, inverse cosine of, what's the delta y? Well, that's 2.5, right? It drops 2.5 meters in delta y. And the distance on the face of the ramp, or the hypotenuse, is d right there. That's 5 meters. Okay, so what is our phi going to equal to? We do a quick little calculation. I get that our phi is going to be equal to 60 degrees. Let's dotted line box that. It's important because that's a key to finding out this this problem right here. It's 60 degrees difference between the angle or the direction of motion and the force that is being done right here. So this right here, 60 degrees is phi. Everybody see how we got that? All right, we just used a little bit of trig. This displacement, that displacement, figured out the angle in between. All right, now I think we can actually solve it, or get close to solving it here. I'm going to take this once again and move it up into the corner so we have a little bit of room. All right, so remember, what's our equation for work? Work is force times distance times the cosine of the angle between them, and we know that angle right now. That's good. All right. So what is our force that is acting right here? Well, the force is really mg, right? It is the weight force applied straight down. We know our distance. Of course, our distance is down the face of the ramp, and that is, well, I'll just call that d for now, and of course cosine theta. So let's actually plug in what our force and our distance are. So the weight is 4970. Well, that's the mass of it, right? Kilograms, of course, times 9.81. That's our g right there. Our distance is 5.0 meters, and our cosine times the cosine of, what's that angle? 60 degrees, right? That should give us our work that gravity does right there. All that's done for us. All we need to do is calculate it out. All right, we did a little bit of, kind of prep work right here to get that. But we know our force. That's gravity. We know our distance, our displacement. Of course, we know our phi because we calculated that. All we need to do is just do a little calculating. What do we get? Well, I don't know what you get, but I get, and this seems like a lot, the work done by gravity is 121,889 joules. All right, seems like a lot, but if you think about it for a second, you've got a pretty massive object right there. All right, and what's causing that to move down? Well, gravity is. That's why I put the little g right there. Gravity is doing the work for us. So it's moving it down the face of this ramp, and it kind of seems like, well, of course it would do, because everything always falls down because of gravity. Yeah, but think about this, though. The amount of work that you would have to do to take a almost 5,000 kilogram lifeboat, that's about, that's like almost like 10,000 pounds, and push it up that ramp would be a heck of a lot. Well, gravity is doing that to bring it down, so that's the amount of joules that gravity is applying right here. So there you have it. It's another application of our work being force times the distance times the cosine of phi. For example 3, what I'm going to do is make that a separate video and kind of explain this, because this one does not have a whole lot of givens, that is, actual values put in here. It's kind of conceptual, sort of, and I'll kind of hash that out in a separate video, but for the time being, we're going to skip that. So you can look for that elsewhere. The rest of this is really just going to be a little further into the notes. Actually, there will be one more example, but just kind of expositing the notes a little bit further. So let's just keep going ahead. To this point, we've pretty much looked at positive work being done, but work can also be done negatively too. If you apply some sort of force that's, you might say, greater than 90 degrees from the direction of motion, you are doing negative work. All right, so our phi right here, the angle that is the smallest angle between the force and the displacement or distance, if that is greater than 90 degrees but less than 180 degrees, we say you do negative work. Think of it like this. If there's a rolling cart right here, it's moving that way. That's our distance right there. All right, if you apply a force to it, kind of like that, I guess I should have written it in red, but that's okay. That's our force. What's happening? Well, you're applying a force to slow the cart down, right? So the force that you're applying is taking energy out of the system right there. So you're doing negative work. And so what we can do is we can make a statement about the net work on a system. The net work on a system. And let me explain that. All right. Sorry about that. So what network is the concept of network is really all the various different works added up. So some of these works right here could be, that could be a positive work that is put into a system. This could be some negative work right here. So we have pluses in front of all of them, but what I prefer to do is add them all up, but then if it's negative, just have a negative in front of that individual work value. So positive work 1, negative work 2, positive work 3, etc. And that gives us the net work, or the sum of all the work or works that is applied to a system. There's an example that I had flashed up there for just a second that I'm not going to do in this video. I'm going to save that for a separate video as well. But the point of that, and I'm going to kind of give you this first, is this idea. The fact that the net work on a system is really the net force on a system times our displacement times the cosine of phi right there. All right, so really, if you can find the net force on a system and the displacement and the cosine, of course, that will give you the net work. So you don't necessarily need to find all those individual works if you just find the individual, if you can just find the net force caused by the individual forces. Multiply that by d and cosine of phi, it'll give you the net work on a system. So that's, for this video, is where I'm going to stop right now. I'll do example 3 and example 4a and b in separate subsequent videos, but I think that's probably okay for the time being. So thanks for watching, and I'll see you on the next video.